Hello class, this is the part B of the fifth example. Hope you had enough time trying to give that a go. So let's get straight to it. We are looking for the rate of change of the base area when the height of the pile is 2 meters. Okay, so let's think about the rate of change of the base area. So part B, we're being told h, the height, is equal to 2. And our goal that we're looking for is the change in the area of the base, so dA over dt. That's what we are looking for. Well, this introduces something new because we're actually looking for the area now, which if you go right to the beginning, we actually didn't work on anything with the area. We all worked with the volume. Okay, so let's keep moving here. We need the area now, or the area of the base of this circular pyramid. It's a cone. So this is a circular base. That's going to be pi r squared. From here we can have dA on dr, which is going to be 2 pi r. Okay, so now we can use this now. We have dA on dr. If we can now find dr on dt, we can cancel these two, leaving us with dA on dt. So we can try and go ahead and look for that. You can pause and give this a go yourself. But as much as you keep trying, it's actually going to be very difficult to find because we don't actually have anything that will give us the rate of change of r, or the radius, against time. So we will not be able to find dr on dt. So let's take a look at what other pieces of information that we have. Well, from the beginning, we saw that in this particular question, h is actually equal to r. Okay, so let's try and use that instead. So instead of a being pi r squared, in this particular example, we know that r equals h, so pi h squared, meaning we can have dA on dH. That's going to be 2 pi h. Let's get rid of this. Oh, let's actually put a, can't use that. So we can actually use dA on dH. Now all we need left to have dt on the denominator is to cancel out dH. Really think about this expression here, dH on dt. That is the change in height over time. That is the rate of change of the height. If you can recall very carefully, that's actually exactly what we were looking for. dH on dt was this expression here. We had already found this in part A. That is dH on dt. So when doing questions such as these, you have to make sure it's very neat so you can look for expressions like these that we may actually not have been looking for initially. So dH on dt, we have dH on dt equaling this expression here. Well, we have everything that we need now because we have dA on dH, that's 2 pi h. So dA on dt, which is what we were looking for, is equal to dA on dH, 2 pi h, times dH on dt, which is 3 on pi h squared. So 3 on pi h squared. Simplifying this, h cancels, and we are left, the pi cancels, and we're left with 6 on h. That's 2 times 3 divided by that 1 h remaining. So dA on dt is 6 divided by h. Well, the rate of change in the area over time, we can find that when h is equal to 2 by let h equal 2. We can now say that dA on dt equals 3. Now, it's important now to put in some units, since we're looking at the area, and remember, everything is in meters, because it's meters per minute. So this is going to be 3 meter squared per minute. And that there is the rate of change of the area over time when the height is equal to 2. So I hope you found all of these examples insightful, and yeah, you gained a lot of skill in understanding such questions and how much information we can actually draw out from something so simple like this. So I hope to see you in the next video. Best of luck.